So, welcome to S1 Lesson 11, Continuous Random Variables, looking at probability density functions and cumulative distribution functions. Before we start, if you have access to the presentation slides, it's a good idea to have a printout of them so you can make notes of what's happening during the video and any thoughts and feelings that you may need to remember after the video. If you don't have access to the presentation slides, it's a good idea just to have some pen, paper and a calculator ready so that you can have a go at some of the examples and then mark your work as you go along to check to see if you've understood the ideas being discussed. So in S1, we've worked through 3 of the 4 major areas of the S1 module. We're now left with the final area of the S1 module, continuous random variables, and in particular we will be looking at probability distribution functions and cumulative distribution functions and the relationship between them today. So a little bit of a recap and an outline of what continuous random variables are. A random variable, remember, is the set of outcomes from an experiment or event. We've met this idea a couple of times throughout the course now. Now, a random variable is continuous when the set of outcomes is continuous, and that is what we mean by that. It can take an infinite set of values within a specified range. And an easy way to identify a continuous random variable is often it's a type of variable that's obtained through a measurement. So all of these are types of continuous random variables. So we've got a length, so the height of a person. We've got weight, it could be the weight of fruit items, capacity, the rainfall in a day, or time, the finished times of a 100 meters race. All of these are, firstly, things that we'd have to measure. Secondly, the height of a person can take an infinite amount of values between 1 and 2 meters, for example. The weight of fruit items could take an infinite amount of values, if we're talking about apples, between, 100 and 200 grams. Okay? Discrete random variables take very specific values, and there is a finite amount of them. So what is a probability density function? Well, a continuous random variable is described by the probability density function. And here we have an example of a probability density function for a continuous random variable x presented as a graph. Now, if we recap the discrete random variable conditions, we have seen that discrete random variables can be represented graphically using bar charts. Here we have distinct outcomes, 1, 2, 3, 4 and 5. And the sum of all these probabilities, so these bars, each one represents a probability, sum of all those probabilities is 1. This could be considered, and we did see probability density functions for the discrete random variable x, it's just that we plot them, a probability density function in this format for a discrete random variable. Now if we apply this idea for continuous random variables, here we have our graph of the probability density function. For discrete random variables, we added up the bars. Those bars represented an area of probability. So if we did the same for the continuous random variable, what we'd have to do is find this area under the curve. And the way we find areas under the curve is by integrating. So that leads to the idea of how we find probability. Now if we have a probability density function defined as we do here, so f of x is defined between some values a and b, then the area under the curve gives the probability as I mentioned previously. So if I want to find the probability between two values m and n, assuming that they lie in this range a, b, then I integrate between the values m and n. There are some further particular probabilities that we could find. We could find a probability x is less than m, at which case we integrate from the lower bound up until our value m. Or we could find a probability of x greater than or equal to m, at which case we'd integrate from our lower value m up to our upper bound b. Let's look at an example. So here's example 1. A continuous random variable has a probability density function. F of x is defined as kx times 1 minus x for x lying between 0 and 1 and 0 otherwise. So I want to find the value of k and then find these probabilities. Okay, so what we know from our definition of continuous random variables is that the integral between the bounds 0 and 1, so that's a and b, of the probability density function k, x 1 minus x, dx. If I integrate between these bounds, because that represents the whole probability, this will be equal to 1. So if I integrate k between 0 and 1, let's rewrite this in a form that I can integrate. So I get x minus x squared dx. This is equal to 1. When I integrate this using square brackets, x integrates to x squared over 2 minus x squared integrates to x cubed over 3. And we integrate that between 0 and 1, and this is equal to 1. So evaluating that now, k multiplied by 1 squared over 2 minus 1 squared over 3 minus 0 squared over 2. Now remember, this is going to evaluate to be 0, but it's good practice. So this should be a 3 here. It's good practice just to demonstrate the substitution. Remember, in later modules where we do integration, not all the functions evaluate to 0 when we substitute 0 in. Now this is all equal to 1. If we evaluate this bracket in one turn using a calculator, we get a half take away a third, which is a sixth. So we get k over 6 is equal to 1. And if I times by 6, we get the value of k is equal to 6. Okay, so now what we can do is we can find the probabilities. Now our first question was probability that our values lay between 0.1 less than or equal to x less than or equal to 0.2. Now this is equal to what the result when I integrate this integral. So I'm going to work from this integral here. So I get 6 multiplied by 0.1, 0.2, the integral x minus x squared dx. So we've already seen that this is equal to 6 times x squared over 2 minus x cubed over 3. So now I can evaluate this. So I get 6 times 0.2 squared over 2 minus 0.2 squared over 3 minus 0.1 squared over 2 minus 0.1 squared over 3. Close the brackets. Now we can evaluate this all in one go and multiply it by 6. So this can all be typed in the calculator carefully in one go, and when we work through this we should get an answer of 19 over 250, which is best left as a fraction. Okay, so let's go on to the next part of the question. Next part of the question wants us to find the probability x is less than or equal to 0.8. So for this question we need to integrate from the lower bound, so that the probability density function is valid for, so that's from 0 up to 0.8. Remembering that we've got 6 as k as the constant, and it's x minus x squared dx. So in reality, in an exam question, we're not really going to face this many questions of the same type, so you won't keep on repeatedly integrating. And we're going to see later a way to avoid this anyway. But just for the time being, we'll just keep on going through this process. So it's x squared over 2 minus x cubed over 3, integrated between 0 and 0.8. So I get 6 multiplied by 0.8 squared over 2 minus 0.8 squared over 3, cubed over 3, minus 0 squared over 2 minus 0 squared over 3. And again, I don't know why I keep saying squared there. It is, of course, cubed. Okay, so close up that bracket. If you carefully type this into your calculator in one go, you should be able to work through that, and you should come to the answer 112 over 250. Oh, sorry, apologies. That's not over 250. It should be over 125, actually. Okay. So final question. Probability x is greater than or equal to 0.7. So this is integrating from the lower bound 0.7 up to its maximum possible value it can be, which is 1. So we're integrating the integral 6x minus x squared. So again, the first part is almost identical to what we've done previously. 6x squared over 2 minus x cubed over 3. But this time we're integrating between 0.7 and 1. So when we evaluate this, 6, first of all, we get 1 squared over 2 minus 1/3 cubed, 1 cubed over 3 minus 0.7 squared over 2 minus 0.7 cubed over 3. And let's just make this 0 here a little bit clearer for you. Closing the brackets. Now if you type this in your calculator carefully and just evaluate that in one go, you should get an answer of 27 over 125. Okay, well I hope that all made sense, because now it's time for you to have a go at one. So here we have a continuous random variable. X has the probability density function. F of x is kx squared for 1 to 4, x between 1 and 4, and 0 otherwise. So I want you to find the value of k. Find the probability x lies between 2 and 3. Find the probability x is less than 2.5. Find the probability x is greater than or equal to 3.2. So if you pause the video now, have a go yourself, and then afterwards check your answer with me. Okay, so welcome back. Let's have a look at the solution to this question. So we started off, we know that our integral between 1 and 4 of kx squared dx, we know that that's going to be equal to 1. So that total probability will be equal to 1. So if I just rewrite this slightly, take the k outside, it's usually a lot easier to work with this way. So k between 1 and 4, x squared dx equal to 1. So when I integrate, I get k times x cubed over 3 between 1 and 4 is equal to 1. And so when I evaluate this, k times 4 cubed over 3 minus 1 cubed over 3 this is equal to 1. So we get 64 over 3 minus 1 over 3, which is 63 over 3, which is 21. So we get 21k equals 1. So finally, just finish off, divide by 21, and we get that k is equal to 1 over 21. Okay, now let's find the probability. X lies between 2 and 3. So here we go, x lies between 2 and 3. Remember what we're going to do, we're going to integrate for our function between 2 and 3, so I get 1 over 21, integral between 2 and 3, x squared dx. We've seen that this integrates to x cubed over 3 already, so it's just then a case of evaluating that between 2 and 3. So we get left with 1 over 21 multiplied by 3 cubed over 3 minus 2 cubed over 3. Okay, so type that into your calculator, evaluate that carefully in one go, and you should come out with an answer of 19 over 63. Let's look at part B. Part B wants us to find the probability x is less than or equal to 2.5. So we're going to integrate from the lowest possible bound of our probability density function, which is 1, up to 2.5. So integrating x squared dx. We already know, of course, what this integrates to. This integrates to x cubed over 3. It's just that we're going to evaluate between 1 and 2.5. So substituting our values in, 1 over 21 multiplied by 2.5 cubed over 3 minus 1 cubed over 3. Okay, so if we enter that into the calculator carefully and evaluate that in one go, you should get an answer of 61 over 504. Okay, finally, the last question was find a probability x is greater than or equal to 3.2. So same probability density function. This time we're going to integrate from 3.2 up to the upper bound, which is 4. So we get integral x squared dx. So this is 1 over 21, x cubed over 3, integrated between 3.2 and 4. So just evaluating that now between 3.2 and 4, I get 4 cubed over 3 minus 3.2 cubed over 3. And if you type that in carefully in your calculator and just work through it, try not to make any mistakes, we should get an answer of 3,971 over 7875. Okay, well I hope that's all made sense. So, the cumulative distribution function. This is a really useful function, okay? Because as you've seen in those previous two questions, it can be a bit repetitive, repeatedly integrating the same function and then just evaluating it for different values. So, the probability density function we've seen defines the function for which the area under a curve is its probability. The cumulative distribution function is a function that actually calculates probability of x less than or equal to x. And actually we've seen some of these before, previously, with the binomial Poisson distribution. So the binomial Poisson distribution, we've seen how to use the tables, but what the tables actually represent are the values calculated by taking the summation of all the probabilities from r equals 0 up to x using the different probability density functions for those particular distributions. So in terms of our discrete random variables, what I'm highlighting in red, that is actually our probability density function. And the way we do it as a cumulative distribution function for the discrete random variables is we sum from our lower value to our upper value, each of the values calculated with this probability density function. It doesn't quite work like that with the continuous random variable, so let's have a look and see how that works. So for a continuous random variable x, if it has a probability density function defined as shown on here, then what we do is we can find a cumulative distribution function by integrating from this lower bound a to x, the function if it was written in terms of t. Now that might seem a little bit strange at first, but it will make sense when we have a look through the example in a moment. Now what this means is once you get a cumulative distribution function for the continuous random variable x, we can define it like this. It's very similar to the probability density function, but you've got to note it's using a capital F. And in lots of areas of maths, a capital letter for a function represents an original function, and lowercase can represent the derivative. So remember, I'm integrating from the probability density function to get the cumulative distribution function. That means I would differentiate the cumulative distribution function to get the probability density function. Anyway, that comes a little bit later in the video. Let's focus on the fact that if I've got this cumulative distribution function, then actually to calculate the probability of x being less than or equal to x, I can just substitute the value of x into that function. And where this is advantageous is you don't have to keep on integrating the same function all the time. We're just actually substituting values into the function. So let's have a look and see how this works. Here we have the continuous random variable x. It has a probability density function 3 over 2 x squared defined between -1 and 1, and it has a value of 0 otherwise. So we want to find a cumulative distribution function, and then we're going to find some probabilities. So let's start with that. So we said to find a cumulative distribution function, we integrate between the lower bound, which is -1, and x, the function defined in terms of t. So we're going to have 3 over 2 t squared integrated with respect to t. So when I integrate this, I get t cubed. I divide by the 3. So instead of having 3 halves, I get 1 half. And we're going to integrate this between -1 and x. So now what happens is we evaluate this And so I substitute in x first of all, and I get half x cubed. And then I substitute in the subtract half minus 1 cubed. And when we tidy this up, we get left with half x cubed. We get minus a half, so plus 1/2. And so f of x, the cumulative distribution function, is simply a half x cubed plus a half. And this is why we changed the variable inside this integral to t, so we can distinguish between t and x, and we integrate up to x so that we get left with a variable in the function. So let's see how we can use this to calculate probabilities. Probability that x lies between minus 0.1 and 0.3. Well, this can simply be calculated by evaluating using our cumulative distribution function for 0.3 and subtracting f of 0.1. So substituting in those values, we get a half times 0.3 cubed plus a half minus a half 0.1 cubed plus a half. And you can see that this is much quicker than having to repeatedly integrate the same thing all the time. If you put this into your calculator carefully, you should be able to evaluate that in one go, and hopefully you come up with an answer 7/500. Okay, so next, find a probability x is less than or equal to 0.1. This is really nice and straightforward because cumulative distribution function is actually designed to calculate that probability immediately. So what we get here is we get f of 0.1. So if I just simply substitute 0.1 in, nothing else, then what we're going to get, f of 0.1 cubed plus a half. And so we type that into our calculator carefully and calculate that in one go, and you should find we get an answer of 1001 over 2000. Okay, so finally, let's find the probability x is greater than or equal to 5. Not 5, sorry, 0.5. So for this we do 1, the total probability, minus the probability of it being less than or equal to 0.5. So a little bit like we use the tables, so I'm just going to do 1 minus f of 0.5. And so when I work through this, I get 1 minus half times 0.5 cubed plus a half. So this then comes out, when you work through it carefully, as 7/16. And you can see using the cumulative distribution function is a lot more streamlined and efficient than having to integrate each time. Well, I hope that made sense, because it's now time for you to try one. So we have a continuous random variable. X has a probability density function 1 minus a half x for values of x between 0 and 2. So you need to find the cumulative distribution function followed by these probabilities. So if you want to pause the video and resume in a moment, and you can check your answer. Okay, so let's have a look at the answer to this question. So we are going to integrate between the lower bound, which is 0, and x, the probability density function written in terms of t, and we're going to integrate that with respect to t. So when I integrate this, I get x, sorry, not x, it should be with respect to t, a little bit of a slip there. T minus, well, when I integrate t, it goes to t squared, so I'm going to divide by 2, so I get minus a quarter t squared. And I'm going to integrate that between 0 and x. So substituting in our values, I get x minus a quarter x squared minus 0 minus a quarter 0 squared. which comes out as x minus a quarter x squared. So f of x simply given as x minus a quarter x squared. So let's calculate some probabilities with this then. Probability that x lies between 0.8 and 1.5. So simply going to calculate cumulative distribution function, substituting 1.5 into that, minus when we substitute 0.8 into that cumulative distribution function. So we're going to get 1.5 minus a quarter times 1.5 squared minus 0.8 minus a quarter 0.8 squared. Stick this into your calculator, work through it carefully, just take your time, make sure you're making no silly mistakes. Should hopefully come up with an answer of 119 over 400. Find the probability that x is less than or equal to 1.2. So this is just simply calculated, just do f of 1.2. So we get 1.2 minus a quarter of 1.2 squared. If we work through this slowly and carefully, just type it in your calculator in one go, you should get an answer of 21 over 25. And finally, probability x greater than or equal to 0.5 can be found by subtracting, doing 1 minus f of 0.5. So we get 1 minus 0.5 minus a quarter of 0.5 squared. Again, just type that into your calculator all in one go, nice and carefully, so as not to make any silly mistakes. You should get an answer of 9 over 16. Okay, well I hope your answers matched up to what I got and that you've been following the video so far. So there's one final thing to look at. That is the relationship between the cumulative distribution function and the probability density function. The cumulative distribution function is found by integrating the probability density function. The probability density function is therefore found by doing the opposite, which is differentiating the cumulative distribution function. Let's have a look and see what we mean by this. Okay, so we're given the continuous random variable x has the cumulative distribution function 2/5 of x cubed minus 1/3 x between, defined for x lying between 1 and 3. We want to find the probability density function. So then the probability density function, p.d.f, is equal to, when we differentiate our original function, so we had 2/5 x cubed minus 1/3 x. So when I differentiate this, I get 6 over 5 x squared minus 1/3. And so f of x is defined, strictly speaking, as 6 over 5 x squared minus 1/3 for x between 1 and 3, 0 otherwise. And it's as straightforward as that. Finding the probability density function is a little bit simpler than finding the cumulative distribution function, simply because it's differentiating instead of integrating. Well, I hope that made sense, because now it's time for you to try one. So we have a continuous random variable x. It has our cumulative distribution function as defined here. What I want you to do is find a probability density function. So pause the video, have a go at yourself, and then resume it in a moment when you want to check your answer. Okay, so let's have a look at the answer. I want to find a probability density function. This is found by differentiating my cumulative distribution function with respect to x. So I have 1/4 x to the power of 4 minus, I believe it's 3/8 x, yep, minus 3/8 of x. When I differentiate this, I get 4 times a quarter, which is 1. So I get x cubed minus 3/8. And so strictly speaking, if we define the probability density function fully, what we get is f of x is equal to x cubed minus 3/8 for x between -1 and 2 inclusive and 0 otherwise. Okay, well I hope the video has made sense and that you've been able to follow it all the way through, because that is the end of the video. All that remains for you to do now is for you to have a go at a probability density function and cumulative distribution function exercise, and then if you try out the assessment 11. Okay, well I hope you found the video useful.